How you doing, physics fans? Welcome back to another video. This one's about entropy, which is a really interesting and important topic in thermodynamics in the universe. So entropy, a lot of people define entropy as a measure of disorder. Personally, though, I don't really like that definition. I think it's a little bit confusing. Like, how do you measure disorder? What does that really mean? So there's another definition of entropy, which I think is a little more conceptual and makes a little more sense to me. And that definition is that energy or entropy is a measure of how spread out the energy in a system is. So if I had a cup of hot tea in a freezer, right? Or in like an ice box, a cooler, let's say. It's, lower entropy actually than if I took that heat from that tea and let time pass and spread it all throughout the cooler, right? When it's spread out more, that will be a higher entropy. So it's a little more conceptual to me. It makes a little bit more sense. But when you use entropy as a measure of disorder, that disorder, the more disordered something is, the higher its entropy. And so it's kind of a similar idea, because the more spread out your energy is, the more disordered something is too. So I think it's but okay, so let's talk about how we use it in thermodynamics. So in any interaction, the total entropy of the universe increases. But I really want to specify actually that it's any real interaction, because in physics we have a lot of ideal things and a lot of theoretical things, and those are, you can have some that are reversible, some that don't increase the entropy. So any interaction where the entropy of the universe, or the entropy of the system or the universe, increases is irreversible. And any interaction that does not increase the entropy of the system is considered reversible, meaning you could undo it, right? So irreversible reactions you can't undo, and reversible ones you can. And these, like I said, you cannot undo them, and these ones you can undo. So for those of you who made it this far into the video, I'll say that the first 3 people to send me their favorite recipe, I'll give 3 extra credit points on the next test. Now, I'm a big fan of baking, but don't all send me baking recipes, because I can't get too fat over this break. Or, I still need to keep in shape and can't get too big of a belly. So, back onto entropy. Let's say I have a container that has 2 different gases in it with a wall between them. So I've got gas A on the left and B on the right. So would it be more or less entropic now or after I move the container and then wait a little while for it to mix? Right? So the question we ask ourselves is, which is more disordered, right? So here it is much more orderly, actually, because I only have gas A on this side and gas B on this way. So there's less ways this can be arranged. And here, there's more ways this can be arranged, because they're all mixed together, because which particle's here, which one's there, what's next to it, there's a lot more that can be done with that. So since there's fewer ways to arrange this, there's lower entropy. Now, it's important to realize that when we're doing this, if I say this is helium and this is neon or something, I picked them because they're both monatomic gases, I can't tell the difference between individual helium atoms, so it doesn't matter if I switch 2 of their places. But I can tell the difference between helium and neon, right? So if I were able to somehow tell the difference between helium atoms, then, and I could number all of them and track that numbering, then we could carry out and say the entropy is higher because you can tell where things are and you can mix it up more if I could just number each individual atom. But because every proton looks the same and every neutron looks the same and every electron looks the same, I can't tell the difference between individual helium atoms either. Every helium looks the same. Every neon looks the same. Every hydrogen looks the same. So it makes it so if I have them in one arrangement and then I just move them all around but put them in the same arrangement, I can't tell the difference. It's like if I had took a bunch of pool balls, put them in a bag, but they're all from different sets and they're all the 8-ball. I probably can't tell the difference between which set they came from, right? But if you took all the pool balls from a single set and you have 1 through 18, then, or 18? It just occurred to me I don't know how many pool balls are in a set. If you pull them out, you can look at the number and say this one's different than that, and I can tell the difference. And so that the order I'd pull them out in would matter. So if you want to measure or calculate entropy based on the number of ways something can be arranged, S, which is entropy, can be found from Boltzmann's constant times natural log of W, where W is the number of ways. So entropy is S, KB is Boltzmann's constant, which we talked about in a previous video. Got its own video, actually. And W is the number of ways that a system can be arranged. It occurs to me that I haven't told you the units for entropy yet. So the units for entropy are going to be joules per Kelvin. All right, so I'm going to call it quits on this video, and I'll see you in the next one. Have a good day.